All right, everybody. Well, thank you for your patience as we let the last few folks arrive. I think we'll get started now. For those of you who don't know me, I'm Samuel Singer. I'm the founder and executive director of Wyoming Stargazing. Thanks so much for being here. Really excited to be doing another year of our World Above the Tetons speaker series. We've got a great lineup of monthly speaker events this year. If you haven't seen the rest of those events, please check out our website. I'll bring you there at the end of tonight's talk to show you who we have lined up for the next couple months. But yeah, some great presentations, as is tonight's. Before I introduce our speaker for this evening, I did want to remind everybody that all of you who are here tonight are entered into our door prizes, which I'll draw at the end of this evening. We've got some locally designed space stickers that we'll be giving away, as well as one of our Eclipse coins that we made for the 2017 total solar eclipse that we had here in the States, as well as an astrophotography print made by one of our board members. Some of you have also purchased raffle tickets to win one of those astrophotography prints, and we'll be raffling one of those off as well at the end of the evening. Without further ado, I'd love to introduce our speaker for this evening. Dr. Roberge is an astrophysicist in the Exoplanets and Stellar Astrophysics Lab at NASA's Goddard Space Flight Center. She received her master's in physics at Johns Hopkins University before receiving her PhD there as well in astrophysics. She's here tonight to tell you all about her research in exoplanets and future space telescopes. Dr. Roberge, thanks so much for being here, and we're all yours.
Super, thank you very much. Right, so as Samuel said, I'm going to tell you something about the amazing discoveries in exoplanets that have been made over the last 25 years. So these are planets around other stars. And when I was in college, we didn't even know they existed. So I'll briefly go over where we've been and where we're going with this very new field of science. And so also for this remote talk, so I'd like to try something a little different. Usually when I give in-person talks like this, I often invite the audience to, ask quick clarifying questions as we go along, and saving longer, more exploratory questions for the end. Now that's hard to do in a webinar. So after the first few slides, I will pause for quick clarification questions, just because I want to make sure no one gets lost at the very beginning, because I use some bit of jargon that they don't understand. Okay, so if you have any quick questions, please type them into the chat window, which I should be able to see. Like at the moment I can see. And I'll just, I think I'm somewhere around slide 4 or 5, I'll pause and take a look at them. And hopefully we'll have plenty of time at the end so that people can unmute and we can have more of a discussion. Okay, so diving in. I can't, diving in. There we go.
Hey, Mom.
Hi. Right, so when I was in college, scientists thought that planets were probably very rare beasts. And it turns out that that's completely not the case. This movie shows a cartoon of the exoplanets known as of several years ago, rendered as if they were all orbiting the same star. And I checked the NASA Exoplanets website the other day, and as of a few days ago, over 4,000 exoplanets have been discovered, most of them using NASA's Kepler Space Telescope. And that's really only the tip of the iceberg. From the Kepler data and from other data, we think there's at least one planet for every star in the galaxy. So that comes to over 100 billion planets in the Milky Way galaxy alone. But what was even more surprising, and really even better, is that the exoplanets we've discovered are extremely varied. And there are types of planets that we don't have in the solar system. For example, there are the huge, incredibly hot gas giant planets orbiting closer to their stars than Mercury orbits the sun. These are somewhat unimaginatively called the hot Jupiters, and they were the first exoplanets discovered. There are warm, water-rich planets about the size of Neptune, another thing we don't have in the solar system. Rocky planets up to twice the size of the Earth. As you might expect, we just call them super Earths. All the way down to Earth-sized planets. Now, those Earth-sized planets may in fact be like the Earth with atmospheres and water oceans, but right now we just don't know. And the reason we don't know is that when we detect exoplanets today, we are actually measuring the effect of the planet on its host star rather than the planet itself. So for example, NASA's Kepler mission stares at stars and measures their brightness. Now, some planetary systems are oriented basically edge on to us, so that one or more of their planets pass in front of the star from our vantage point. And that's called a transit. Let me see, can I play this again? Yeah. So when that happens, the light from the star dips by a tiny, tiny amount. And from that, we calculate the size of the planet. So right now, in the vast majority of cases, all we can measure about exoplanets is their orbit, their size, and mass. And in the best cases, if we're lucky, we get all three. So as one of my colleagues has said, they're basically small black shadows to us right now. Okay, so all right, so let me just take a pause here, take a quick look at the chat questions. I think I'm seeing, well, what's that on the intro slide? The very title slide? Ah, that's an artist conception. An artist conception of a particular planet that was discovered with the Kepler Space Telescope that is roughly Earth-sized and is orbiting about an Earth-like distance from its star. And so people have speculated whether it might in fact be Earth-like, a habitable planet, as this was rendered in that first artist conception. However, as I hope you just heard me say, we don't actually know that it looks like that. I think in the rest of my slides, I think I've been more careful to label what are artist conceptions and what isn't. Yeah, okay, but Samuel actually answered that one anyway. Okay, so, right, okay, moving on. So we really want to go further than small black shadows and find out what the atmospheres of these exoplanets are actually like. So the first big step in this direction will come with the James Webb Space Telescope. It's seen here in this video in the clean room at Goddard, in fact, in 2016. So the science instruments are behind, you're seeing the primary telescope mirror right now. The science instruments were in the package on the back of it. The primary is gold, in fact. It is, in fact, well, it's not solid gold, but it's coated with an extremely thin layer of gold for maximum sensitivity at the infrared wavelengths of light that this telescope observes. So the telescope and the instrument package are currently at Northrop Grumman in Redondo Beach, California, where they were connected to the additional supporting hardware, the spacecraft, and final tests were performed. And very soon, in fact, I think they just started packing it up. The observatory will be packed up for shipping via boat to French Guiana for launch on a European Space Agency rocket. And all things going well, that'll happen this fall. So JWST will probe the atmospheres of many large gas-rich planets like Jupiters and Neptunes and really tell us a lot about what they're made of, including hopefully those mysterious warm Neptunes and warm sub-Neptunes. So all of these discoveries lead us to a more ambitious goal, answering the ages-old question, are there other Earth-like worlds out there? So we know that Earth is unique in the solar system in that it has a moderate temperature, liquid water, and abundant surface life. So if we're going to ask, so we already know there are no other Earth-like worlds in the solar system. So to answer this question, we need to look outside the solar system. And it's a question that fascinates scientists and the public alike. So for example, the 2017 discovery of 7 Earth-sized planets orbiting the nearby star TRAPPIST-1 created really an astonishing amount of public interest. The day of the announcement, there were 2.5 billion non-unique users talking about TRAPPIST-1 on social media. Now, NASA is very active in social media, but I think even our own public affairs people were taken by surprise. Okay, but to get to the goal of finding out if some of the small exoplanets out there are really like the Earth, then we'll need different observation techniques. So small black shadows won't do it. We need to move to basically fuzzy colored dots. We need to actually see the planet itself and then analyze the light that's coming directly from it. So the hard part about that is that planets are faint and they're located right next to bright stars. So imagine you're trying to see an airplane flying near the sun. You can't do it until you put your hand up and you block out the bright sunlight. And that is basically what an instrument called a coronagraph does in a much, much more extreme way. This movie shows the current state of the art. And now this is not an artist's conception, that is data. It is a composite of several images taken over several years with a coronagraph on the Keck telescope in Hawaii. So the bright central star, can you see my mouse at all? Yes, you can. Okay, so the bright central star would be in the center, but it's mostly blocked out. This boiling of brights, we call them speckles around it. That's the residual starlight that didn't get completely suppressed. But here's the goal. You see around it these 4 dots, 1, 2, 3, 4, that are actually going around the star. Those are 4 enormous gas giants larger than Jupiter, orbiting very far from their host star this time. And this is actually another type of planet that we didn't know could exist. Okay, so why aren't we doing that right now for Earth-like planets around sun-like stars? So here is the observational challenge. Okay, the Earth is ridiculously faint compared to the sun. It's 10 billion times fainter at optical wavelengths. Okay, now that's just a number. So people often compare it to trying to look at a firefly next to a spotlight. Unfortunately, that's actually not extreme enough. So this is more accurate. So so the Luxor skybeam coming out of that hotel in Las Vegas is the brightest artificial light in the world. If that's the sun, then the Earth is the brightness of 2 fireflies-ish. But astronomers have observed things that are about that faint already. The real problem is that that incredibly faint source is right next to the bright star. So viewed from a distance of 33 light years, that's actually 10 parsecs. So astronomers don't use light years. That's not that far away. That's really the solar neighborhood still. The apparent maximum separation between the Earth and the sun is 0.1 arc seconds. So that's about the width of a human hair viewed from a distance of 2 football fields. So imagine trying to see those fireflies if they were sitting basically on top of the Luxor skybeam. We need to suppress the bright light from the host star by a really extreme amount before we can see a faint Earth-like planet next to it. And there's no telescope and instrument that we have today can do that. Okay, so how are the needed tools being advanced? So the next big step in coronagraph development will happen with the Nancy Grace Roman Space Telescope. And this is NASA's next strategic astrophysics mission after the James Webb Space Telescope. And there's a picture of Nancy Grace Roman from a while ago. She recently passed away in the last couple of years. She was a fantastic lady. I actually got to meet her. So, and she's often called the mother of Hubble. She was one of the key people who actually pushed Hubble, got NASA into this science business, and pushed Hubble, out, into space. Well, not literally, obviously, but she really, made sure it got done. Now Roman, that is named for her, is a 2.4 meter telescope that is in fact much like Hubble, but it is largely focused on studies of dark energy. However, Roman will also carry the first advanced coronagraph into space as a technology demonstration exercise. So this is a preliminary simulation of multicolor direct imaging of a nearby planetary system with the Roman coronagraph. This was made by my then postdoc, Maxime Rizzo. So the input planetary system for this model was, for the simulation, has a sun-like star, which would have been there, orbited by a warm Jupiter at 2 AU from the star. And just to make sure everybody knows, 1 AU is the Earth-Sun distance. So there's the planet visible as a blue dot here. And so there's still this haze of light here and here. And this comes from, this is a prediction of what we would see for the interplanetary dust coming from asteroids in the system, how it would collect into these sort of two lobes that are leading and trailing the planet. So the Roman coronagraph is designed to push down to Jupiter and Neptune-sized planets orbiting in the warm inner regions of nearby sun-like stars. But even more importantly, Roman and its coronagraph are a technological stepping stone to the real prize. Okay, that telescope, 2.4 meters, is just too small to really study Earth-like planets around sun-like stars. To do that, we need a much more ambitious space telescope. So in January 2016, NASA began a concept study for such an observatory, the Large Ultraviolet Optical Infrared Surveyor, or LUVOIR for short. It's a working title, and it's not French. Make sure you say it like a pirate, LUVOIR. So, and I was the study scientist for this concept study. So it is an idea for a mission in the tradition of the Hubble Space Telescope with very broad science capabilities. And as you might expect from its name, it's ambitious and will also enable a revolutionary range of general astrophysics and solar system studies. Here are a few technical highlights of LUVOIR, just to geek out for a little bit here. Okay, so the architecture is scalable. So we designed two variants of the observatory. LUVOIR B is large with an 8-meter diameter primary mirror. And LUVOIR A is really large, 15 meters in diameter. That's over twice the size of the James Webb primary mirror. Okay, and like Hubble and Webb, both LUVOIR variants will carry several kinds of instruments at once. We designed 4 candidate instruments during the study: an advanced coronagraph, that would be the workhorse for the exoplanet observations, an ultraviolet multi-object spectrograph called LUMOS down here, a wide field camera, because you always have to just have a camera, and Pollux, which is a different kind of rather complicated ultraviolet instrument. And the design of this one was contributed to us by the French Space Agency. Okay, and both LUVOIRs feature modular design. So this is to enable in-space servicing and upgrading of the instruments, as was done for Hubble. And this will also make integration and testing of this very large observatory on the ground somewhat easier, for sure. Okay, so in sum, LUVOIR is a powerful and hopefully feasible observatory to tell the story of life in the universe. And after 3.5 years of study, we gave our final report to NASA headquarters and the National Academy of Sciences in August of 2019. Now, since then, an eminent group of scientists and technologists that were assembled by the National Academy have been considering priorities for future US astrophysics, both in space and on the ground. And this is a long-standing, once-a-decade process called the Astrophysics Decadal Survey. And all of NASA's great observatories went through this process before being chosen for development. So we should find out what the Decadal Survey thinks about the priority of building LUVOIR within a few months, early this summer. So as you can imagine, I'm eagerly, nervously anticipating that report drop. Okay, but it takes a long time to develop a large space telescope. So now let's pretend it's the late 2030s. That's about the soonest we think we could launch this. And this is what we want to see with LUVOIR, an image of a planetary system that looks like our solar system. So this is, in fact, a simulation of the inner solar system viewed in visible light from a distance of 12 parsecs with the coronagraph on LUVOIR A. So there's Jupiter is booming bright. In fact, it probably would saturate. And Venus is visible just outside the inner edge of the coronagraph starlight suppression region. It has a weird, somewhat unsurprising green color. That's an instrumental effect that is correctable. But right here, there's the pale blue dot that we're looking for. Okay, but pictures of planets, as attractive as they are not the real goal for LUVOIR. We want to actually measure the planet's atmosphere and the surface conditions using the light that's reflected from the planet. And furthermore, we want to see if there are signs that the planet has life on it. So as I mentioned earlier, the Earth is unique in the solar system in that it is the only planet that's teeming with surface life so abundant that it's strongly affecting the planet's atmosphere. From a practical point of view, this is probably the only kind of life that we can both detect and recognize from interstellar distances. So I often hear people say like, oh, you're so focused on Earth and, what if it's different than Earth? Well, if it's different than Earth, we'll be able to tell, but we have to have something, a thesis to design to. And so our focus, astronomers' focus on Earth-like planets is not entirely self-centered, but it is instead a practical consideration. Okay, so let's consider Earth's atmosphere as our template. And this plot shows visible and near infrared light reflected from the entire Earth, a disk integrated spectrum. So the y-axis up and down here would be brightness, with bright at the top, faint at the bottom. And then the light is spread out by wavelength or color, bluer over here to redder over here. So this rise in brightness right here on the far left is literally our blue sky. This narrow dip right here is caused by absorption of sunlight by molecular oxygen, and we're currently breathing this waste product of photosynthetic life. And all of these deep, broad absorption features come from water vapor, pointing to liquid water on the planet's surface. And then finally over here, there is part of a methane feature. In our atmosphere, methane is mostly produced by bacteria in the guts of our livestock and in swamps. So the large amounts of oxygen and methane that we see in our atmosphere could not be there without life. So here's another way of looking at astronomers' search for life. So we'll get data like this, as well as a whole lot of additional information about the planet and its star. We'll try to explain what we see with detailed physics and chemistry. And if we can't, we'll turn to the other science left in the building, which would be biology. Okay, but LUVOIR would also have a supporting role to play in the search for life nearby within the solar system. So the discovery that many of the icy moons in the outer solar system have subsurface oceans dramatically expanded scientists' thinking about potentially habitable environments. Now this image here, taken with Hubble, shows an ultraviolet aurora from Jupiter's moon Europa, observed, I said that with Hubble. So this light originates from the breakup of water vapor in plumes emanating from the surface. And these plumes can provide a glimpse into the deep ocean. Now, these subsurface oceans must be heated from below, probably by geothermal activity. And geothermal vents at the bottom of Earth's oceans harbor life forms that don't depend on sunlight for energy. So most scientists, I think anyway, think that Europa and other ocean moons are probably the best chance to find life in our backyard. Okay, now here are simulations of how this auroral emission might look to LUVOIR. So what our plan would be is that we could monitor Europa and other ocean moons of the outer solar system with flexible timing over many years and determine the frequency of this activity. Okay, so you can learn a lot more about the mission concept, the LUVOIR mission concept on our website, including our full range of science goals. I didn't say anything about our general astrophysics science goals, of which there are a great many. There's a lot of technical detail. You can see our team members, and somewhere there's a link to an archive of popular articles about LUVOIR. Okay. All right, so cruising along here. Anyway, so heading towards the end, I want to emphasize that finding out if an exoplanet is inhabited really calls on a wide range of expertise, from biology to technology. And the search for life isn't the domain of one scientific discipline alone. It draws in all the parts of NASA and beyond. So here's a sampling. So for example, studying the impacts of the sun on solar system planets through space weather is key for understanding what kinds of stars can be hospitable for life. Then, of course, as I said, the Earth itself is our best and only template for a habitable and inhabited planet, and it really is the model that guides all our endeavors. Okay, then Mars itself was once warm and wet, making it a place to look for evidence of past life forms. But it's also, maybe more importantly, a test case for understanding the evolution of habitable conditions. Like, you know, under what circumstances do you get to stay habitable? Then, again, as I mentioned, the ice-covered ocean moons of the solar system's outer planets, like Europa before, and this is Enceladus, are the most promising places in the solar system, I think, anyway, to look for current life. And everything we learn from all of those studies guides the search for Earth 2.0 and life among the stars. Okay, and so to conclude with the NASA exoplanet mission swoosh, exoplanet studies began with ground-based telescopes, which are still playing a major role. New kinds of observations were enabled using Hubble, the Spitzer, and Kepler space telescopes. Right now, the TESS mission continues to search for exoplanets around nearby stars using the transit technique, which is the same technique that Kepler used. And Webb will greatly advance our ability to probe the atmospheres of large exoplanets. And after that, there is a possible path stretching out over the next decades that leads to the first survey for planets that could be hospitable for Earth-like life. And furthermore, if that kind of life is not extremely rare, then we'll have a fighting chance of finding some. So we're in a really exciting position right now of possibly answering an age-old question about our uniqueness in the universe, and maybe even more importantly, finding out if we're even asking the right questions. So, okay, thank you. So that's all the prepared material I have. It looks like there's heaps of time for questions. So over back to you, Samuel.
Thanks so much, Dr. Roberge. Yeah, if anybody has any questions, feel free to unmute yourself and you can go ahead and ask them.
Kind of the obvious one, what's your expectation of a positive result later this summer?
Oh, from the Decadal? Oh, gosh. I'm cautiously optimistic, I guess is all I can say about that. But the National Academies keeps a very close hold on the deliberations of the Decadal survey, and there has been no leaking, much to my disappointment.
I didn't think it would be like the Academy Awards. I thought perhaps you might be hearing some signals that might be pushing it in a direction or the other, which is why I asked.
No, unfortunately, they really do they really run a tight ship there. No leaks. And it is a little like the Academy Awards, actually, I suppose. If we were doing this in person live, usually the Decadal survey is presented in a live conference at the National Academies, but I assume that probably will not happen this year. It'll be a video con.
And it's been a while since I was involved with PCAS, but what's the level of funding look like in the last 4 or 5 years? Are we getting positive contributions in terms of funding, or
PCAS? What is that?
Or the President's Council on Science and Technology?
Oh, I don't know about that particular council much, but the skinny budget, as we call it at NASA, the president's preliminary budget came out, I think, today. And I did notice there was quite a decent little increase in funding for NASA, about 6% or so, which is pretty good.
Good. That's a good.
Of course, but we won't, without the detailed budget, we don't know what the administration intends to spend that increase on. So we won't find that out until May.
Best of luck.
Yes, thank you. Let me just let's take a look at the chat here. Deborah wrote a question, a giant planet close to its star, question mark, but I'm not sure what that was referring to now.
I think that was back to that picture on the intro slide.
Oh yes, I should label that one also. I should also label that one artist conception just to make it absolutely clear. Oh, though I think it is in fact supposed to be an artist conception. I think it's of the planet Kepler 193b, in case anybody cares.
This is Deborah. I thought you had mentioned that there was a gas giant closer to its star than Mercury, and I thought,
Oh yeah, there are a great many of those.
well, doesn't the gas burn off, blow up?
In some cases it does, in fact. However, and it is thought that in some cases these very warm, and if you took a Neptune, you can't completely evaporate. You can't really boil off a Jupiter atmosphere's worth of gas that way. But if you took a Neptune mass or a sub-Neptune mass planet and moved it very close to the star, where we see some planets like that orbiting, you can have significant atmospheric loss. There's been some preliminary observations showing that. So it's possible that some of those super Earths that I talked about, these solid planets that are larger than the Earth, may in fact be the cores of evaporated Neptunes, which is pretty strange to think about. And it's really it's really hard to figure out what a planet like that would look like. You took the core of Neptune and heated it, stripped off the hydrogen and helium and heated it up. There would be a lot of water, but how that would manifest itself is really quite mysterious. Hopefully JWST will tell us something about that. The Webb Space Telescope will tell us something about that in the coming years.
Thank you.
Yeah. So what are some of the competing projects in the Decadal survey? Yes. So when NASA initiated, where did I put it? Wherever. I can't remember. All right, so when NASA initiated the LUVOIR study in January 2016, they also did 3 other studies of potential future large space telescopes. One of them was called LYNX, and that would be an X-ray telescope. It has some very limited exoplanet applications, but it's really not for exoplanets. It's for studying hot things, black holes, active galactic nuclei, supernovae, things that go boom. And then there was also the Origins Space Telescope, which was a far infrared telescope. So that's for studying the opposite end, cold things. And in particular, it would be good for sort of tracing the ingredients of habitable planets throughout the universe, from their, like how water goes from out, the interstellar medium into planet forming systems and then into planets. And it could do some studies of exoplanets, but not do so much on the truly Earth-like planets around sun-like stars. And then the third one was HABEX, and HABEX is the Habitable Exoplanet Observatory, and it's actually much like LUVOIR. It has very similar science goals, but it differs in quantity. HABEX is only a 4 meter, has only a 4 meter diameter primary, so it does a lot of the same stuff that LUVOIR would do, but quite a bit less of it. And there are some things that are just not possible, particularly in the general astrophysics area, with a telescope with a mirror that small. So it is in fact more focused on exoplanets, whereas LUVOIR is intended to really be sort of a much more equal marriage between astrophysics and exoplanet studies. So those are the candidates. We don't like to say competitors because we were all very get along with each other during the studies and help each other out. So candidates, not competitors, is what we'll say. In a perfect world, eventually those would all happen and they would represent a new generation of NASA great observatories the way Hubble, Spitzer, Chandra, and Compton, actually, NASA's original great observatories spanned almost the whole electromagnetic spectrum. And these would represent like a new generation of great observatories to span like a huge range of wavelengths. Okay. How many pixels wide would the exoplanets be on the LUVOIR? Like 2. They're not going to be resolved. To spatially resolve, to actually resolve the surface of an Earth at 10 parsecs, you need a telescope that's more like, oh gosh, what was it? I don't know, hundreds of meters in diameter, not 15. So they will be unresolved fuzzy dots. So how many pixels they span just depends on how many pixels you want to put underneath the resolution element. And if you want to optimally sample, I don't know if you guys know this. You might know this if you're amateur astronomer. The point spread function of the telescope, you put 2 pixels underneath for Nyquist sampling. So I should emphasize they're really unresolved. Carl Sagan's pale blue dot, totally unresolved. However, that being said, you can learn something about the surface features, even with the planet not being resolved as a disk. So for example, if you could monitor the planet over over a few days. And if it was like the Earth, you would see the brightness of the planet vary as continents, oceans, and clouds come in and out of view. And you can analyze that and look for the periodicity, what is repeating over and over. And from that, you could tell the day-night cycle of the planet. And there are some experiments using comparably bad Earth data that would show that you can, in fact, you could tell like the fraction of cloud cover, the fraction of ocean cover, and the fraction of land. So you can make sort of like a very coarse, an extremely coarse map of the planet that only had longitudinal information. You couldn't tell anything in the latitude direction. Okay. You mentioned some specific characteristics about some exoplanets, example, some with water more than just mass. How do we know that? Yeah, okay, so for that particular case, I think that you're referring to when I was talking about those warm Neptunes, or those cores of evaporated Neptunes, you're right, we don't know that they have a lot of water on them. What we do know is that they should, simply based on what we know about how planets form and what we know about Neptune and Uranus themselves. So I would say it's I should have said before, it's a thesis more than not an observational fact, but we'll find out soon. Hopefully we'll find out soon if they are water rich. I mean, because Uranus and Neptune are not called ice giants for nothing. So they actually do contain a lot of volatile material like water. If these planets are anything like that, they should have a lot of water. Any thoughts on David Kipping's idea of using the Earth as a gravitational lens to direct light to a space-based collector? He calls it a terrascope. Yes, I'm familiar with that concept. It sounds hard. And it's not completely clear to me how well you can retarget that. If you're basically, you have to line it up. You have to line up. I'm not sure how he lines it up, but you're lining up the telescope and the Earth and the target star, and the Earth has to be in the right position. So you don't get to just point it anywhere you like. I haven't read his stuff closely enough to figure out what's its actual efficiency. If it's not very efficient, then you would really need to know exactly which star to point the telescope at before you go doing that. So chances are you probably still need to do a survey, a LUVOIR-like survey first, to find the telephone numbers of where your actual Earth-like planets are before you go trying to point something like that at it, which is extremely difficult to point. So that's what I think about that. I think it's, yeah, it's a neat idea, but I think it's harder than it sounds and not that efficient from an observational point of view, if that makes sense. Hubble was serviced via the shuttle and humans doing spacewalks. How would LUVOIR be serviced? We are agnostic on that point, because you may have noticed, while we can think of how to assemble a telescope in space, the infrastructure to do that doesn't exist at the moment. Now, there are parts of NASA that have been working on robotic servicing. So like a refueling or servicing of satellites in low Earth orbit. I'm sure that there must be somebody in the human spaceflight program who would be thrilled to, do a Hubble-like servicing endeavor again with humans. But thinking about it, probably the best way of doing it is actually to use both. So telepresence would probably be best. Use the robots driven by humans. So you is probably the right answer. Sort of a best of both worlds scenario, if I had to guess. However, I will say the infrastructure for servicing something like LUVOIR doesn't exist. But I mean, some people would say, I should note also too, James Webb and Roman and LUVOIR, if it happens, all will be out at the Sun-Earth Lagrange 2 point, not in low Earth orbit like Hubble is. So out further from Earth, where it's nice and cold and dark and quiet. So to service that with robots out there, they would have to be autonomous because the lag time would be quite long for communicating. If you did it in low Earth orbit, that might not be the best place, just because it's so crowded. If you did it, possibly the best place would be somewhere like where NASA is planning to put the Lunar Gateway. So in a very high, orbit, something between Earth and the Moon, further away from the Earth, where it might be the right place to do it. Close enough to get there easily and to communicate with the robots, but not so close that you're worried about all the junk in low Earth orbit. That would be my guess. Right, but at the moment, we have designed the telescope. Our problem was to design the telescope to be serviceable, not to figure out on NASA's behalf how they would service it. That would require a big effort from other parts of NASA to figure that out. Okay. I think those are all the questions I see in the chat.
I think there's just one other about if
did I miss one?
the project wasn't funded initially, is there an opportunity to reapply?
Yeah, next decade. Next decadal. Although, hopefully a certain amount of technology development would continue nonetheless, no matter what happens. This isn't the first time that scientists have proposed a telescope to study, to find and study Earth-like planets around sun-like stars. There have been others that were put forward to earlier decadals, which didn't happen. I think in one case it sort of started and then didn't get the blessing to continue. It was a bit early. It was called Terrestrial Planet Finder, and it was quite some time ago. It was too early probably for that particular experiment. And then a concept that was similar to LUVOIR, but different in some critical ways, called At-Last, was proposed to the previous decadal. Did not get the blessing. Roman got the blessing last time. So you know, these things take a long time and you have to be patient and persistent. And in between, the decadals just keep picking away at it as best you can and maturing the concept and the technologies as best you can until you're finally ready. But I do think that at some point, NASA will need to do something like this New Worlds Telescope, LUVOIR or HABEX. These days, I just call them LUVEX because they really are sort of variants on a theme. Because this question about whether there are Earth-like planets and life out there, this question is not going away. It's been around for hundreds or thousands of years, and it isn't going away. And you know, scientists there've been many planning exercises and studies and roadmaps over the last 20 years. And I'd say the community consensus is that this is the next step. So it's hard, but not too hard. And it has the right kind of flexibility to do the initial survey, the initial reconnaissance. So, okay, so what are some things you considered for the LUVOIR that you eventually had to drop from the proposal? Well, we would have liked, there were a few people on our science team who wanted this to be even bigger than it is. In fact, we started at 16 meters. But we ended at 15 because as far as we can tell, 15 meters, that's about the very biggest single telescope that you can pack into any of the future heavy lift launch vehicles, even the big ones that are upcoming. Like, so LUVOIR A fits into the NASA Space Launch System Block 2B, which is kind of down the road a piece. It fits very nicely. It fits into a Starship, the SpaceX Starship. LUVOIR B fits into a bunch of things. It fits into Starship with quite a bit of room to spare, which is nice. And it could fit into the basically today's generation of heavy lift rockets with 5-meter diameter fairings. That's kind of one of the reasons that we did 2 variants, is because we wanted to use the scalability of the architecture to show that we were flexible to a exciting but uncertain future in launch vehicles. So that's one thing. So we're at 15 meters because, you know, we didn't want to take the leap beyond 15 meters, which would actually probably require you assemble it in space. And if we're not certain about the infrastructure for servicing this thing in space, we most definitely are not ready to think about the infrastructure we need to assemble something like this in space. I mean, we assembled the International Space Station in space. That's my virtual background. But, you know, compared to LUVOIR, you know, LUVOIR is a very high precision instrument compared to the International Space Station. And it needs, yeah. So what other things did we sacrifice? We would have liked to push the wavelength range of the telescope a little further into the infrared, out to 5 microns. It would have been nice for the exoplanet spectroscopy. But doing that would have meant that we would have to make the telescope colder, or else there would be too much background radiation from the telescope itself to observe at those wavelengths. As it is now, the LUVOIR telescope is actually heated to basically room temperature, will be heated to room temperature. And we're doing that basically to protect our ultraviolet sensitivity. That's critical for a lot of the general astrophysics that we want to do with this. And you have to be incredibly careful about contamination control for ultraviolet telescopes. And the best way to do that is to keep it hot. Keep the mirrors hot so that nothing will condense on them. No water, and in particular, no sticky organic goop that outgassed from every piece of wire or plastic or electronics in your telescope. So so we had to make a choice. We could get 3 more microns on the infrared end, or we could put the entire ultraviolet bandpass at risk. And we decided that that wasn't something we wanted to do. So, what is your main focus of the knowledge that you're personally interested in studying about the exoplanets? Okay, well, that's interesting because, believe it or not, I have never studied an exoplanet. My personal research is actually in planet formation. So I study these disks of gas and dust around nearby young stars, where we can pretty much see now actually that planets are forming right now. That's my personal research. However, I'm interested in planet formation partly because I'm just interested in planets. So I have always been fascinated by sort of the possible diversity of worlds out there. So it was very easy for me to basically sort of dive in here and basically take the search for Earth-like planets and the search for life, take it to heart. But given that I study planet formation, I do sort of stand in between exoplanets and astrophysics, which was actually quite convenient for me, as a sort of trying to manage the science team, which was composed of a range of scientists from all the way from black holes to, people who study Jupiter. So are there any future ground-based telescopes that are being considered for exoplanet research? Absolutely. The major ground-based facilities are doing exoplanet research right now. In future, coming up pretty soon on the ground, should be, as soon as they get the money together, a new generation of the extremely large space telescope, the ELTs, extremely large telescopes. So one example is the 30-meter telescope that's being designed and planned by basically a consortium led by the Universities of California. There's the Giant Magellan Telescope that would be in Chile, and that one's led by a consortium led by the Carnegie Observatories. And then there's the European Southern Observatory version, which is the actual one that's actually has the acronym ELT, Extremely Large Telescope. And that one's supposed to be 40 meters in diameter. So these things are enormous. And I believe they've started building some of the pieces for them, but I don't think any of the projects quite have all their funding lined up yet. But these observatories will do lots of exoplanet observations, but they are complementary to these space-based observatories like LUVOIR and HABEX for various reasons that are kind of complicated to explain. If you want to study Earth-sized planets in the habitable zones of low mass stars, red dwarf stars, that you probably can do from the ground with these future extremely large telescopes. But to really study the planets that are most like the Earth-sized planets in the habitable zones of sun-like stars, that can probably, it appears in many analyses over decades that you need to go to space for that. You need to get out of Earth's atmosphere for that more difficult observation. But it's fine. These two, it's good when there's complementarity between the ground and space. Between the space-based telescopes and the ground-based ones, we should cover all the stars. So, except those really massive O and B stars, which we don't think can really have planets anyway. Okay.
Looks like there was one more question a little ways up about obtaining spectra in the atmospheres of exoplanets?
Yeah, that's exactly what we want to do. That's exactly what we want to do. We'll get an image like this. We will drop down the spectrograph aperture right there, right on the blue dot. We'll take that light, disperse it, and get something that looks like this, but with noise, but noisier, because this is a model. So that's exactly what the goal is to get spectra of the atmospheres of these planets. Yeah. Right, and like I said, Hubble is actually obtaining some kind of low quality spectra of hot Jupiters now. The James Webb Space Telescope will get much better quality spectra of Jupiter, Neptune, sub-Neptune sized planets. And then hopefully someday we'll have something like LUVOIR that will get spectrum of the atmosphere of a truly Earth-like planet. And it'll look like this, but much crappier. Just noisy. Yeah. So, okay, does that, is there any artificial intelligence or complex software processing to isolate planets from noise in the stars? In fact, there are. Yes, even after we've suppressed the star by a huge amount, we'll need to do post-processing on the data. And that's kind of assumed that we've done that here. Basically, there are several techniques you would use. One of them is kind of complicated. One of them is basically to make an incredibly good, use data from a bunch of stars that don't have planets to create a really good model of what the telescope, the shape of what the telescope is doing to the light. And then use that to take out some any residual leakage, starlight leakage around the coronagraph edge. So yes, it's not artificial intelligence. It is complex mathematics. It's complex algorithms. It's not artificial intelligence. I think probably there is a machine learning application here, though. In those algorithms, they could be. I don't know. I don't really. It's not my specialty. I don't know a lot about it, but I expect that generating those models of what the telescope is doing to the light entering it, the telescope and instrument, actually probably is a decent problem for a machine learning algorithm. So, but if you want to talk about that, you'll need to ask somebody else. If you want a detailed talk about that particular topic, you'll need to ask someone else. I don't know that much about it. Okay, did I get them all now?
I've got one for you.
Okay.
So I teach a high school astronomy class here in Jackson. And of course, the kids like to talk about intelligent life elsewhere in the universe, and then just possibility of any life on some exosolar planet somewhere in our galaxy. And they often ask me when we're going to have the first positive detection of life on some exosolar planet. And I kind of shrug my shoulders and talk about the timelines of the launch of the next few space telescopes and ground-based telescopes. We're going to be looking for these signatures, but I'm curious if you have an estimate of when we might.
I'm pretty much in the same boat as you. It's probabilities. I mean, I can tell you when capabilities will could come online. JWST should launch this fall, knock on wood. And while I don't, JWST wouldn't really be able to detect Earth-like biosignatures as we understand them. Could it detect some kind of other kind of biosignature? I don't know, maybe. I don't know what it looks like. So how can I say? So I think that's probably a long shot though, and as the kind of the point of LUVOIR and HabEx is to like stack the deck, to focus to focus in on the kinds of planets that most closely resemble the one that we know can be inhabited. So, which is our, that's what we've got to go on. So I would think as time goes on through where's the swoosh, through the swoosh, I mean, it's possible, maybe with Webb, maybe but I don't even, it's hard to even know, because it would have to be some kind of biosignature that was extremely different from what we have from Earth-like. How we would even recognize it as a biosignature, I'm not completely certain. Roman, not so much. Roman is a technological stepping stone to get to here, where we've tried to increase the odds as much as possible by focusing in on the known. And as I said, but once we do this, I think we'll have increased the odds, but I don't know by how much, because I don't actually know where we're starting from. We don't know. The only thing, I mean, if you wanted to take a completely fairly meaningless, wild guess, you could look at the solar system and say we've got 3 planets that are about the size of Earth that are basically in the habitable zone of the star, and one of them is inhabited. So is the probability 1 in 3? Maybe. Or but that's actually, from a statistics point of view, that's total bull to do something like that, to calculate a probability off from one success. So it's a reconnaissance, it's an exploration. It's what we have to do a lot in astronomy. We don't get to control our experiments the way that a lot of other sciences can. We can't go into the lab and cook up a test tube of something and study it. We are, as you well know, we're exploring the universe. We don't get to change it. So it's a, I don't know, I guess you'd call it a mission of discovery. So that was a really long-winded answer that says, I don't know, and basically what you said. So, on the other hand, though, I am fairly optimistic about the chances of life on other worlds, simply because there's a ton of real estate out there. Planets are common. And the ingredients of life are common. We are made out of we're mostly made out of the 4 or 5 most common elements in the universe. So just on that basis, I'm fairly optimistic.
As am I.
Yes. In 10 years, at the time of the next review, what do you want to see in the next generation proposals? Well, what I hope to see in the next generation proposals is next decade is not LUVOIR, because we already got the blessing, but one of our other compatriots from the new grade, the suite of new grade observatories, maybe the X-ray one, LINX. So probably, HABEX and LUVOIR being so similar to each other, I rather expect that if this decadal survey says, yay, verily, we should do a New Worlds telescope, a direct imaging mission to study, potentially Earth-like exoplanets, they'll tell us, they will probably tell us to both y'all combine your best ideas from both designs and give us a fresh one, a single fresh one. I actually bet they would do that. They should do that, actually. So, so those, if either of us got a blessing, probably we'd end up with some sort of hybrid. And so maybe next time, maybe that X-ray telescope. So, LINX. With the renewed interest in the moon, does it make sense to have a telescope located there? A radio telescope, yes. Any other kind of telescope? No. It's really very dusty. It's the in that sense, the Earth is better because we have a thick atmosphere and higher gravity. It cleans, most dust doesn't just float around everywhere forever in our atmosphere. It settles. That doesn't happen on the moon. The moon's super, super dusty. and it's continually being, bombarded with micrometeoroids, kicking up more dust. Dust on your telescope, as I'm sure you're well aware, is not something you want. Radio telescopes, on the other hand, don't care about that at all, given that they're not so much telescopes as they are antennae. So it makes a good deal of sense to put a powerful radio telescope, I think, on the far side of the moon. But other telescopes, no, it's not a terribly good idea. It's much better to just be in space. So that's what I would say about that.
Well, Dr. Roberge, thank you so much for building all those questions. I really appreciate it, as I'm sure everyone else does.
Do you have time for a couple more quick ones?
Sure.
Yeah, sure.
So
I'll keep going.
These are just different questions that came to my mind.
Mhm.
3 different ones. One was in terms of planet formation, which you're interested in. Is there a difference, say, a planet formation out in our Orion part of the galaxy compared to other parts as you get closer to the center? Is there something more unique? And I don't even know the size of our part. Like, how far away was TRAPPIST?
Well,
and-
quite close, a few parsecs. It's
I have a couple other questions. Let's do this
yeah.
one first.
Okay. Interesting you bring up Orion, actually, because Orion is a high mass star forming region. It's got some OB stars in it. And we think actually the solar system formed in quite a similar environment. You're right, to the Orion Nebula, a fairly crowded, high energy environment. And we know that basically because of the abundance of radioactive elements that we have in the solar system. There was a supernova not too far away. And that's kind of interesting because the closest star forming region to the sun is Taurus, and that's a low mass star forming region. So it's actually quite different from the environment in which the solar system formed in, and yet it's the best studied. And most of our planet formation and star and planet formation, the detailed modeling is based on data from Taurus. So it's actually, in some ways, yeah, we understand as a general process, in some ways we understand the formation of planets in environments that are rather different from the one we formed in. So anyway, sorry, but I'm not sure if that was that actually your question?
Well, I was actually just thinking of
Yeah.
this whole area, this whole part of the galaxy compared to more like the center, but that's too far away.
Yeah, we don't know
we
much.
don't have any idea at this point.
Well, we don't know much about that. Although there should be anyway a sort of an elemental gradient of elements, through the galaxy, with because the everything heavier than hydrogen and helium formed in stars, and in the center of the galaxy there were a lot more stars and older stars. And so I'm speculating here for a minute. It's possible that the star forming environments closer to the center of the galaxy are more enriched in heavier elements than the environment we formed in. So what the consequences of that would be is probably more and larger rocky planets, I guess, maybe, but that's a total guess. We don't really know. It's just a total guess speculating on what we do know about the solar system's formation. So.
Yeah, that's for the future.
Yeah.
So the other 2 quick questions are, these are the Webb telescope, James Webb is going to Lagrange point 2. So we were talking about servicing and whether it could be robotic if it needs servicing. And that's going to be the same you're thinking about with LUVOIR
Well, Webb was not in fact designed to be serviced.
Right. So, but it's,
So,
yeah, but
so it's just,
LUVOIR is going to be, needs to be serviced, or Roman, and they're pretty far away. So
they are.
I can't imagine human servicing of those.
No, that would be unlikely. L2 is pretty far away. But well, first of all, yeah, so I should make it clear. So Webb was not designed to be serviced. I'm kind of sad about that, actually. Roman kind of is. And for LUVOIR, we think servicing is a feature, not something that, you know, this is how Hubble has been, you know, actually, interestingly, as a point for you, today was an important day for professional astronomers. Today was Hubble Proposal Day. For cycle 29, the 29th year of people writing proposals to get time to use Hubble. That was today, 8 p.m. was the deadline. You can see all the funny memes about it on Twitter. There's a hashtag called like Hubble Proposal memes. It's pretty funny. But the reason that Hubble is still oversubscribed at the 8-to-1 level, they're like 8 times, people are asking for 8 times more time to use it than there is available, is for 29 years, is because it's been upgraded. Telescopes haven't changed in some fundamental way. Telescopes haven't changed that much. I mean, you know, the Palomar is like, how old is Palomar? It's coming on to 100 years old, and it's still a fine telescope. The thing that changes is the instruments. And so that's why Hubble, it's a, you know, to a certain extent is a bog standard telescope, but the instruments were upgraded, you know, 4 times, 5 times over the course of that 29 years. And that's why it's still a cutting edge facility. And that's why ground-based telescopes are so, you know, remain cutting edge facilities for such a long time, over many, many decades. So for LUVOIR, our team really embraced that philosophy. We want, for us, servicing is part of the telescope's capability. It's science, it's a feature, it's a scientific capability, a feature, not a bug. So yeah, you wouldn't do human servicing probably at L2. You would want to, I think you'd want to, it would not take much propellant, much energy to move a telescope from L2 to like a lunar type orbit, like a gate, you know, like near the lunar gateway. The delta V required for that is quite low. You're not deep in Earth gravity well. So I think the best thing to do would be to, like, you know, take it back and forth, take it to the shop, fix it up, send it back out.
It's a long distance, but you're saying out there, once you start being able to move things, you're going to be able to move them.
Yeah, well, we're not in a huge rush, right? To get there. Like the James Webb Space Telescope will take some months, I think, to get from, you know, from Earth to L2. Nobody's in a particular rush. So you don't need much delta V. The hard part is getting out of Earth's gravity well.
Is that a big risk on the James Webb Telescope, the fact that it can't be serviced?
Let's hope not.
But is that I mean, that's so far, that is, if the hardware breaks in any way, it's not going to work out there.
Yep. Yes. I think if that happens, while Webb was not designed to be serviced, I think if something like that happens, I think a lot of people will get really creative really fast and figure out how maybe they could do it anyway. There's been a few cases where, you know, NASA has managed to make their telescopes do things they really weren't designed to do. Like when Kepler, for example, it was down to one gyroscope. All its gyroscopes died over the course of the mission. It was down to one. Now, theoretically, you can't point a telescope with only one gyroscope, only one axis of control. But they figured out a way to actually keep using it for several years more, even with some what you would have considered essential hardware broken. So, and that actually wasn't the first time that we've done that. when the gyroscopes seem to be they're always a pain. They're always the thing. They're sort of the telescope killer when they die. Hubble's gyros are getting pretty bad too.
So my last question is your funding from NASA? In other words, if you don't get funded and there's no funding on LUVOIR, are you funded going forward yourself?
Wait, you mean the telescope concept?
No,
mean-
your actual funding. You're a
Oh,
Goddard.
me? Oh,
Yeah.
yeah. I'm a civil servant scientist at NASA.
Mhm.
So if LUVOIR doesn't happen, I will do other things. I could actually do some astronomy for a change, which I haven't had time to do in basically 3.5 years because I've been doing the LUVOIR study. I could do some astronomy. I could work on a different telescope concept. I'm actually currently helping out with some things for Roman myself right now as well too. That's my other job. So no, there's plenty of work. There's plenty of things to be doing, and we don't have we have more work than we have people to do it anyway. So I won't be lacking for stuff to do.
Mhm.
But I want to spend the rest of my career working on LUVOIR, and if I'm lucky, I will see it launch before I'm pushing up daisies.
Thank you.
Sure. Is there also a contractor for LUVOIR? Oh, there would be, because no big NASA observatory is built only by NASA. First of all, all of our big ones, Hubble, not Kepler, not Spitzer, maybe a little, not Kepler, not TESS, Webb for sure, Roman for sure. These are all international observatories. So for example, the European Space Agency is a partner on Hubble, Webb, Roman. I think JAXA, the Japanese Space Agency, is a partner on Roman. I think the Canadians are kicking in a little bit too. So for sure, this would be it would be an international partnership. Then on top of that, there's always major industry involvement from the aerospace industry. So for example, the prime contractor for the Webb was Northrop Grumman. And we had industry partners helping us during the LUVOIR concept study. Actually, it's Ball Aerospace. That's not too far from you, the ones in Boulder. Ball Aerospace, L3 Harris, Lockheed Martin, and Northrop Grumman were all helped out to one degree or another during the LUVOIR study. So we rely on them to help us develop our technologies and to, actually build things too. NASA doesn't build everything in-house. So yeah, so they're really very multifaceted, which I think is a virtue. It makes them hard to manage in some ways, from a project management perspective, but I think you get, the value of the collaboration is worth it. Okay.
All right.
Okay, we good?
Thank you so much again,
Sure.
Dr. Roberge. That was fantastic.
Yeah.
So we just have a few minutes before 8:30, and so I want to do the drawing for all the door prizes and the raffle.
Right. Should I stop sharing now so you can show what you wanted to show?
Sure, that'd be fantastic.
Yeah.
Thank you. But before I get to those door prizes, I just want to make one quick announcement that on Sunday, we have a special virtual stargazing program that we're going to be hosting with Wyoming Stargazing, but with a South African astronomer. So it's during the day, which is pretty cool. So he's going to show us a bunch of stuff in the southern hemisphere sky from South Africa, and we'll be able to show you those images in more or less real time at about 3 p.m. Mountain time. And so it'll be on Zoom. The link's on our website. So if you want to see some cool stuff from the southern hemisphere, tune back in on Sunday. All right, so those door prizes. Let's do those first. So we're going to start with the Eclipse Coin. Oh yeah, virtual backgrounds do such weird things to images. So there's the Eclipse Coin. You can notice that it's got a little hole in the center of it to project the partial part of an eclipse. We've got several coming up in the next few years, so it'll be handy. The winner of that Eclipse Coin is Alan. So Alan, just send me an email to samuel@wyomingstargazing.org with your mailing address, and I will get this Eclipse Coin on its way to you. All right, now for this space sticker made by Holly Sage Art here in Jackson. Winner of that sticker is Tim. Same to you, Tim. Just send me your mailing address to samuel@wyomingstargazing.org and I'll get that off to you. One more sticker here. Oh, that one's not showing up. Oh, there you go. A little tricky there. Winner of that sticker is Ken Burns. Congrats, Ken. Same to you. Just please send me your mailing address and I'll get that off to you. We're also going to draw one door prize for an astrophotography print. We've got lots of different prints to choose from. And so if you're the winner for this, you can go to our website, choose which print you'd like, and then we'll get it in the mail to you. And we can either do a 12 by 12 with the square prints, and there's a 8 by 12 in the rectangular prints on one of the other pages. So the winner of the Astro print for the door prize is John M. Congrats, John. So again, just send me your preference to samuel@wyomingstargazing.org and we'll get that out to you. So now for the raffle drawing for an astrophotography print. These are for the folks who actually bought raffle tickets. And the winner of the other astrophotography print is Liz Mosley. I don't know if Liz is on the call with us right now, but I know how to get a hold of Liz. She's one of our other board members. Well, again, thank you to everyone for being here this evening. Really appreciate you joining us. And Dr. Roberge, again, thank you so much for joining us. And we've got an astrophotography print for you as well. So you can pick one out and let me know which one you'd like and give us a mailing address and we'll get that to you. So thank you so much for your time. And thanks again to everybody and hope to see you all on Sunday for the virtual stargazing in South Africa. And with that, have a good night, everybody, and take care.
Good night. Thank you.
Very welcome.